This video will introduce concepts related to magnetic fields. We will learn how to sketch and interpret the magnetic field patterns produced from a bar magnet, a straight current carrying wire, a circular current carrying loop of wire, and a solenoid. In addition, we will explore how to use the right-hand grip rule to determine the direction of a magnetic field from the direction of a current. A magnet is an object that is able to produce its own magnetic field. A magnetic field is a region where a magnetic object will experience a force. Magnets will have two poles, a north-seeking pole, one that is attracted to the north pole of the Earth, and a south-seeking pole. The magnetic field produced by a magnet can be visualized through the use of magnetic field lines, which are labeled with a capital B in diagrams. So let's begin with the magnetic field for a single bar magnet. Magnetic field lines have various properties that they must follow. First of all, the direction of the magnetic field at any point is tangent to the field line at that point. Magnetic field lines always form closed paths and are directed from the north pole of a magnet to the south pole. So even though some of these lines seem like they have an open end in this diagram, they will form a closed path. Another property is that the field lines never intersect each other. This 3D animation of a bar magnet further highlights that the field lines do form closed paths everywhere rather than ending at the poles, and that the field lines do not intersect. In addition, the strength of the magnetic field is proportional to the density of field lines. So as we can see on the bar magnet, the field lines are closer together near the poles, so the strength of the magnetic field is greater near a pole. These magnetic fields will exert forces on magnetic objects that are placed in the field. Here we will consider bringing two bar magnets closer together. We notice that two like poles will repel each other, while two unlike poles attract, similar to how positive and negative charges interact with each other. We also see that the forces between the magnets increase as they get closer together. This is because the magnetic field is strongest near the poles of the magnets and will exert greater forces at the poles. If we consider the magnetic field lines of each magnet, we find that the magnetic field lines bend away from each other between two like poles. The north poles would tend to follow the path of the field lines, so the magnets will repel each other rather than coming together. With two opposite poles, the magnetic field lines join together and become denser between the poles. This shows a stronger, nearly uniform magnetic field, pushing the poles together and showcasing the attractive force. Furthermore, a compass can be used to examine the presence of magnets. The needle of a compass is a small bar magnet on a pivot so that the needle can rotate. When a compass is placed near an external magnetic field, the needle will experience forces that will align it with the direction of the magnetic field. In particular, the direction from the south pole to the north pole of the needle will give the direction of the external magnetic field at that point. Magnetic fields can also be created by moving electric charges. Recall that a current is a flow of electrical charge carriers, so a straight wire carrying a current will produce a magnetic field around it. In particular, the magnetic field lines are concentric circles that are centered on the wire. However, as soon as the current stops, the magnetic field will also disappear. The spacing between successive circles increases from the center of the wire, which shows that the strength of the magnetic field decreases as we move away from the wire. In addition, the strength of the magnetic field can be increased by increasing the current in the wire, as we show in this short animation. However, the direction of the magnetic field is dependent on the direction of the current in the wire, and we can use the right-hand grip rule to determine this direction. The right-hand grip rule works as follows. Take our right hand and point the thumb in the direction of the conventional current. Imagine that we grip the wire with our fingers, then the direction in which the fingers curl around the wire gives the direction of the magnetic field. So when we have an upwards pointing current like in this image, the thumb will point upwards, and our fingers will curl anti-clockwise, indicating an anti-clockwise magnetic field. In addition, we will often see these two circular symbols used in diagrams, which represent the direction of the quantity that they are representing. So in this example, the current. A circle with a dot in the center indicates a direction pointing out of the screen or page, while a circle with a cross indicates a direction into the screen. We can think of this as viewing the ends of a dart being thrown out of and into the screen. By using the right-hand grip rule, for a current leaving the screen, we point our right thumb towards us and see that the current will produce a magnetic field that points anti-clockwise, and a current entering the screen will produce a magnetic field that points clockwise. Now let's take the straight current carrying wire and bend it to form a circular current carrying loop. This loop is orientated so that the current at the top of the loop points out of the screen, and points into the screen at the bottom of the loop. Using the right-hand grip rule at different points of the wire, we can see that the magnetic field direction changes as the wire curves. But notice how the magnetic field lines all point in the same direction inside the loop. If we do this around the entire loop, we find that the magnetic field lines are more concentrated in the center of the loop than outside the loop, indicating that the magnetic field is stronger inside the circular loop. If we now take a long straight current carrying wire and bend it to form multiple loops as follows, we form a solenoid and effectively multiply the strength of the magnetic field. Each turn of the solenoid acts like an additional current carrying loop and contributes to the magnetic field in the center of the solenoid. If we look at a side view of the solenoid, where the current comes in from the left and exits on the right, we will see a nearly uniform field that is concentrated in the center of a solenoid and a field that is weaker on the outside. We can use this alternative version of the right-hand grip rule to find the direction of the magnetic field around both a circular loop and a solenoid. By curling the fingers in the direction of the current, the thumb will point in the direction of the magnetic field lines inside the solenoid. So in the given solenoid, curling the fingers in the given current direction will give a magnetic field pointing to the right as shown. Notice how the magnetic field for a solenoid is similar to that around a bar magnet, so we can assign north and south seeking poles to the solenoid. However, unlike a magnet, the magnetic field of a solenoid can be turned off if there is no current, or reversed if we change the direction of the current. In addition, the magnetic field strength around a solenoid can be increased by increasing the current in the solenoid, and by increasing the number of loops per unit length of the solenoid. We will now provide a final summary of the key understandings from this video. We saw that magnetic fields are produced from magnets and from moving electric charges, and they can be visualized through the use of magnetic field lines. In particular, this video showed the magnetic field patterns for a bar magnet, a straight current carrying wire, a circular current carrying loop of wire, and a solenoid. We found that magnetic field lines always form closed paths, and the density of field lines at a point is proportional to the strength of the magnetic field at that point. For a bar magnet, the magnetic field lines are directed from the north pole to the south pole of the magnet. For a current in a wire, the right-hand grip rule is used to determine the direction of the magnetic field from the direction of the current. We use this version for a straight wire, and the following version for a circular loop or solenoid. This now concludes our video on magnetic fields. Thank you for watching.